the authors. So take it away.
Yeah, thank you. So I'm going to talk about effective Littlestone dimension. This is work by Valentino, Sasha, and Tomasz. Just to reiterate, I'm not on this paper. Unfortunately, they couldn't be here today, in part due to some visa issues. But they were kind enough to make these slides, and I'll try to do them justice. So as you can imagine, this is a paper about online learning. So let me just kind of refresh your memory on the rules of the game. So it's a game between a learner and an adversary. And the game is really defined by a hypothesis class of functions from some domain X to the binary set 0, 1. Okay, and so throughout the paper and throughout the presentation, let's think of X as the natural numbers. Okay, so unlabeled data comes from natural numbers, gets labeled by 0 or 1. And so at the start of the game, an adversary thinks of a function in H, which is kind of the true labeling function, and then a sequence of unlabeled data points, okay, unbeknownst to the learner. And the way the game actually goes is that the adversary feeds an unlabeled data point to the learner. The learner responds with a predicted label for that data point. And then the adversary reveals what the true label actually was and gives it another unlabeled data point to predict on. Okay, and so in the event that the learner's prediction was incorrect, it incurs a mistake. Okay, then the learner just got a new unlabeled data point, makes another prediction, possibly incurs another error, and so on and so forth. Okay, so the mistake count of the learner is just the total number of incorrect predictions that it makes on this sequence of unlabeled data points. Okay, and we say that this hypothesis class is online learnable with D mistakes if there's some strategy that the learner can do that ensures that regardless of the adversary's choice of F and the unlabeled data, it's going to make at most D mistakes. Okay, so for infinite sequences of unlabeled data or for arbitrarily long finite sequences, same thing. And so, as I'm sure you're aware, this is just the classical notion of being online learnable with D mistakes. Where this paper really comes in is to require the learner to be computable. Okay, so typically we kind of are very hands-off when we talk about learners. It's kind of okay for them to be very abstract mathematical functions. What we're going to do now is actually force the learner to be algorithmic. Okay, so we're going to ask the learner to actually be implementable by some Turing machine. And we're going to talk about two kinds of computable learners. So the first kind is a total computable learner that always halts on every single training set. Okay, even the ones that aren't realizable by H. That's a total computable learner. Then there's a partial computable learner that halts on realizable training sequences, but maybe stalls on some non-realizable training sequences. Okay, so there's kind of a little bit of ambiguity. If you were making this definition, there's a little bit of ambiguity of how you should define this. These are really the two natural notions. Okay, kind of a stronger and weaker notion of computability. So the only difference, maybe you stall on these non-realizable samples. Okay, now, let me go back a sec. Okay, so as you know, Littlestone trees are very important for online learning. So that's just a tree where nodes are unlabeled data points, and then edges leaving those nodes are possible labels for the data. Okay, so for instance, the leftmost path on this tree would be, you see the unlabeled data point 5, then it gets labeled by 0, then you see the unlabeled data point 7, the label turns out to be 0, kind of and so on for the other paths. And so let's just say that my hypothesis class right now is indicators of all the natural numbers. So just a spike of 1 at every possible natural number. Can you find a non-realizable leaf for this Littlestone tree? Probably you can. It's the one where I take the path of 1 from 5, then the path of 1 from 9. So this couldn't have been realized by H because there's no hypothesis in H that ever outputs this label 2 times. Okay, so that's the idea of realizable versus non-realizable leaves in this tree. And now the Littlestone dimension of D, I'm going to give you maybe a slightly unusual definition. It's the smallest D such that any D plus 1 tree has a leaf that's not realizable. Okay, so you might be familiar that it's the largest D such that I do have a tree that's realizable. I think you can see that this is equivalent. And in a couple minutes, you'll see why this kind of equivalent but different definition is a little better for our purposes. But that's the Littlestone dimension. Okay, so any D plus 1 tree has something that's non-realizable. At least some of the depth D trees can be realized. And by a classic result of Littlestone, as I'm sure you're familiar, the Littlestone dimension is exactly the smallest mistake guarantee that you can actually achieve. Okay, and so this is in the classic setting where a learner is just some kind of abstract mathematical function. So now let's get into the results of this paper. So what I'm going to do is, in different circles, I'm going to have different conditions on a hypothesis class, and then I'm going to relate them with implications or not implications. Okay, so this first condition is that your hypothesis class is online learnable with some finite mistake bound and with a partially computable learner. Okay, so this is the Turing machine that always halts on realizable data. Maybe it stalls on non-realizable data. So that's this condition. I haven't told you any results yet. Another condition that you might have on a hypothesis class is that it has finite Littlestone dimension and every function in your class is computable. Okay, so that's what I mean by computable. Just point-wise, every function in my class is computable. So if I'm online learnable with any kind of learner, certainly I have finite Littlestone dimension. It's not too bad to show that if I have a computable learner, even in this weaker sense, all of the functions in my class have to be computable. Okay? The reason why is that if this wasn't the case, then the output of my computable learner is never going to be equal to, let's say, some function f in my class. And then wherever its output is not equal to f, I make that the next unlabeled data point. And so I'm constantly incurring mistakes. Okay, so wherever my output is not f, I feed you there and you incur another mistake. Okay, so it's easy to see computable online learning, even in the weak sense, tells me that every function is computable. The reverse direction turns out not to be true. This is a result of Hazrati and Ben David, which you might know was actually one of the best papers here at ALT 2 years ago. Okay, so this is an existing result. And so this tells you that Littlestone dimension is kind of not picking up on everything. Okay, even if I'm additionally forcing all my functions to be computable, the Littlestone dimension kind of is not the right dimension for these purposes. Another condition that I'll introduce now is the stronger version of computable learning. Okay, so this is total computable online learning, where my learner always halts, even kind of on data that I'm not allowed to see, even on non-realizable training samples. Okay, so certainly that implies the weaker partial computable online learning. Now I'm going to introduce a new dimension. So this is the effective Littlestone dimension, or you might kind of think of it as the computable Littlestone dimension. Okay, this is one of the key things that's introduced and studied by this paper. And this is the smallest d such that I have an algorithm that actually identifies the non-realizable leaves in d+1 depth trees. Okay, and this is the reason why I gave you kind of a weird definition of Littlestone dimension a couple slides ago, because now I can kind of effectivize it. I can make it computable by just adding the word algorithm. Okay, so this actually gives me evidence of trees that are not realizable by my class. Okay, so now I have a new circle that's hypothesis classes of finite effective Littlestone dimension. So how does this interact with my strong and weak notions of computable online learning? So it turns out you can show that if you have this strong version of computable online learning, you do have finite effective Littlestone dimension. Let me try to give you the proof idea. Let's say I have a total computable online learner that always makes at most d mistakes. Okay, now you give me a d+1 tree. What I do is I give the root to the learner makes a prediction, and I say, whoops, the true label is actually the opposite one. So now it incurs a mistake. I do the same thing at every single node, and I end up at a leaf where my learner made d+1 mistakes, okay, by just after the fact saying that my learner was always wrong. And this leaf can't be realizable because I just said that I have a mistake bound of d. Okay, notice that I'm really crucially using that my learner is total computable. Right, because at some point I hit it with a non-realizable training set, and it still had to give me a prediction. Okay, so I have at least one implication for effective Littlestone dimension. Whoops. Now it turns out that finite effective Littlestone dimension doesn't imply total computable online learning. In fact, it doesn't even imply this weaker partial computable online learning. And they're able to find a counterexample, even for the case in which effective Littlestone dimension is 2. Okay, so even effective Littlestone dimension, it's not exactly the right dimension for us to understand computable online learning. And it's kind of interesting we can find a counterexample of such small effective Littlestone dimension. Rough idea, kind of diagonalize against all possible computable learners. Another thing they show in this paper is that finite effective Littlestone dimension automatically implies that all of your functions are computable. Okay, so certainly I have finite classic Littlestone dimension, but it implies that all of my functions are computable. I'll just quickly say this is by induction on effective Littlestone dimension. Base case is pretty trivial, but inductive step is pretty involved. I'll just mention it's by induction. One more result. My clicker's fighting me here. Okay, one more result. In the special case in which your effective Littlestone dimension is 1, this actually does suffice for computable online learning. In fact, even in the strong sense of total computable online learning. Okay, so that's just for the special case in which your effective Littlestone dimension is 1. And then one last result I'll give you. This one's colored in blue because it's not written down in the paper, but they just say that it's a result that they have that you can show, is that partial computable online learning does not imply finite effective Littlestone dimension. I asked them, what's the rough idea of the proof? They said it's another diagonalization argument. You just diagonalize against all the possible Turing machines that could be witnesses for finite effective Littlestone dimension. Okay, and then one thing I'll mention, I'll end on this, is that with the arrows we have, this actually gives us a separation between total computable online learning and partial computable online learning. Okay, because I have an arrow from total to effective Littlestone dimension. I don't have an arrow from partial to effective Littlestone dimension. And so that means for the two notions of computable online learning, you actually have a separation. So you have some classes that you can online learn with a mistake bound, but only if you're allowed to stall on some non-realizable samples. And you kind of can't replace that stalling even with just outputting junk. So that's, I think, kind of an interesting separation. And those are the main results. Thank you.
Questions for the non-author?
I'll do my best.
So what does this effective Littlestone dimension characterize at all? Does it do anything? I guess beyond establishing the separation?
Yeah, so one thing that it does that's cool that they didn't put in the slides, but I think is pretty cool, is in the last section of the paper they show, if you consider kind of a different version of online learning, where before I give you unlabeled data, I give you some upper bound on all of the unlabeled data points that you're going to see. Okay, so before the game starts, I just save a note. I'm never going to give you an unlabeled data point that's more than a trillion or Googleplex.
Okay.
In that version, the effective Littlestone dimension actually is exactly the mistake bound you can get with a computable learner.
I see.
You just kind of need this upper bound to sort of search over all possible things you could see.
Okay.
So, but it's cool. There's no dependence at all in this upper bound. It can just be, kind of cosmically huge. But
I see. It just has to be finite.
Yeah, it has to just be finite.
Okay, I have a stupid question. Why is it called effective?
Yeah. So computability theorists, as far as I can tell, effective just kind of means computable.
Okay.
So they're like, let's effectivize this thing. Another thing they talk about in the paper is like an effectively open set, which means an open set where I have kind of a computable sequence of open balls that's equal to that set. So it's kind of for any point in that set, I'll eventually pick up on the fact that it's in that set. But yeah, they just kind of use effective to mean computable.
I see. Okay. So, one other question, which maybe is half-baked, since I'm not super familiar as familiar with commutability theory as I should be. Does it make sense to look at restricted cases where the adversary also has to be computable or is bounded in some way?
That's a good question. Yeah, I mean, I guess the question is, what is the input to the adversary?
I guess if every function in the class is computable, that is sort of also a restriction.
Oh, because they're paid. Yeah, that's true. Yeah, that's a good point.
Yeah.
But also the learner is also a restriction with learners as well, isn't it?
Yeah, no, I think it's a very interesting question. Yeah, I haven't thought about it. I guess you could imagine like what's the input to the adversary? I guess maybe the size n, and then it has to pick the data set of size n. Yeah, it's interesting. I haven't thought about it.
Okay, great. Let's thank the speaker.